In this video, I will give an overview on ARIES. ARIES is a widely used recovery method for disk-based database systems. So this algorithm or variants of it are used in almost all disk-based database systems. The algorithm operates in three major phases. There's the analysis phase, there's the redo phase, and there's the undo phase. For the moment, I will assume that there is no such thing as a checkpoint. If you don't know what a checkpoint is, don't worry. I will explain it later on. We don't have it here at the moment anyhow, which for the algorithm means if we have our log file, and this is the first log record in the log file, we have to read all of the log file. We start from the oldest log record and read it sequentially up to the last log record. So this is a crash again, as in previous videos. After the crash, the database is able to restart and triggers the ARIES algorithm. It starts recovery. The first thing we do is we read all of the log file. That is what happens in the analysis phase. So the purpose of the analysis phase is to determine the set of loser transactions. Again, that is a set of transactions that need to be undone. And the second purpose is to find out what is the starting point for the redo phase. That is the second phase. In the redo phase, the idea is we repeat history, which means whatever change should have been applied to the database store, we are going to apply it again if necessary. So what happens typically in a database buffer is that some changes are only applied in the database buffer, which means in main memory, but they don't find their way to disk. So in this phase, we make sure, in the redo phase, we make sure that the changes we applied before the crash really find their way into the store. Again, not necessarily on disk, but every page we see in the database buffer in main memory has the state that existed before. That is done in the redo phase. It starts here from this point in time, and that is the earliest possibly dirty page. So the earliest discrepancy that might have existed before. That is a point in time where we need to reapply changes. And from this point in time, which is determined in the analysis phase, this point, we again read the log forward till the last log record. Once we are here in this position, we are in exactly the same position as we were in when the database crashed. Still, the database is not necessarily consistent because at that point in time, when the database crashed, it could have been that there were some transactions running. And we remember we have the ACID properties, especially the A property, which implies all of the changes of a transaction are committed or none of them. If we had a transaction at this point in time that did not commit, we must undo its changes. And that happens in the third phase. So undo here is only applied for the loser transactions. Only the non-committing transactions, only the changes done by those transactions are undone. And that happens in the third phase, and that must happen from right to left, starting from the newest log record, from the newest change of those transactions to the oldest. And then it depends on when did the first loser transaction actually start. This is this point in time, which we talk about in more detail in a moment, but that is the point in time where I have to go back to in the undo phase. So important to note at this point in time is really that in ARIES, redo means I redo each and every action. I do not differentiate between winner and loser transactions. All of the changes are redone. So when I'm here, I have all changes applied to the database store, at least in the database buffer, and this includes loser and winner transactions. It's not only that I redo the winner transactions, I redo all of them for multiple reasons. We will talk about that. But for the moment, just keep that in mind. Winner transactions are redone, but loser transactions as well. And in the undo phase, the actions done by those loser transactions are actually undone again. So it sounds weird that I do some work here that I then undo again for the loser transactions, but it's actually more efficient and a better algorithm in this case. Let's look at this in more detail. We need some helper data structures, two actually. One is a transaction table and the other is a dirty page table, the DPT, as I will call it. Transaction table is coin TT. So what do the different fields here mean? It's actually very simple. In the transaction table, I have this primary key transaction ID. That's the key of the transaction. That's globally unique in the database system. And that helps me identify each and every transaction that is run in the database system. The second field is called last LSN. This is the most recent log record seen for this transaction. So in other words, it's the latest change done by this transaction. So it might have been that there were other changes done by that transaction before. So if the transaction starts, it looks like this. It does a change, it does a change, it does a change. For each of them, we write a log record. So this might have been 42, log sequence number 42. Then here we have, 110, and here we have 567. So what the table records is this last change operation we've seen for this particular transaction number 1. And this is updated throughout the algorithm. We always update that field last LSN. In the dirty page table, it's also relatively simple. We have a primary key, page ID. This is a unique key. So as learned in the videos on database storage, there is some hierarchical scheme here for those IDs. I denote them with simple integers here for the moment. So here is a page 42 and it has an entry for the recovery LSN. What is the recovery LSN? That is the LSN of the first log record that made this page dirty. In other words, the earliest change done to this page. So what happens in the algorithm is whenever we see a page that's not yet in this dirty page table, then we put an entry there and put also the entry of the corresponding log record, which also implies if there's a second change to that page, there is no update to this number here. This is the first change to this page that was done, and we keep it at all times. The ARIES method does not change those recovery LSN. Those are other structures that change this entry. ARIES itself is not going to change that. For us, it's just important to understand whenever we see a page for the first time, whenever we see that there was a change applied to this page, we must put it into this dirty page table. So for all of what I'm explaining in the following, it's important to understand this assumption here. And that is a database page may contain changes from losers and winners at the same time. So two concurrent transactions may operate on the same page. And I scribbled down similar examples already in my previous videos, which introduced the different types of logging, which introduced how to log in general and the different error scenarios. There I explained it already, where you have a page 42 and then some change was done by transaction 1. Another change on the same page was done by transaction 2. And then it might happen that T1 commits and T2 aborts. So this commits and T2 aborts. As you have two concurrent transactions operating on the same page. In other words, we have a degree of concurrency that's smaller than the page size. We do not lock a single page. We have a locking mechanism that allows us to operate two transactions concurrently at the same time, which means we have typically something like tuple-wise locking. Tuple-wise locking. In addition to that, the database buffer, just to make sure we don't miss it because I already explained that before, database buffer is allowed to use the following strategies. It can use steal and it can use no force. Those are the strategies applied here. Still, ARIES is going to work. So steal means a page may be evicted even though it's used by an active transaction. If a dirty page is evicted, this means that its contents have to be written back to the store. That is what happens, and that is what is allowed for in this method. And the other thing is no force. No force means when you write something to a page in a database buffer, you do not have to necessarily write it back to the underlying disk. Now, whenever you change something in a database page that sits in the database buffer, you do not have to immediately write it back to the disk as well. That can happen at a later point in time. So all of these three things are used in the algorithm. It's tuple-wise locking, there's steal, and there's no force. If you don't require these three properties, you can actually use a simpler algorithm than ARIES. Yeah, so when you really need to implement recovery, you really want to think hard about these things, whether you really need them. If you don't need them, maybe a simpler algorithms will do. But at the time when ARIES was invented and people thought about the algorithm, they made the decision to have these properties, to have these assumptions. Tuple-wise locking is okay. Steal is fine, so any database page can be evicted, and no force is also used, so you don't have to write back dirty pages immediately. And that is the assumptions we're going to make for ARIES. So let's look at the log records in detail. I did a separate video on that already, but let's look at how this is done in ARIES. You have a previous log sequence number. So for any given transaction, this allows us to have a backward linking of log records. Whenever we write out a log record for a specific transaction, we write down this transaction ID as in the transaction table shown above. Yeah, so this is a unique ID again. Once we see the log record, we understand, aha, this belongs to transaction, say whatever, 42. And then here there might be a backward link to another log record. It's worth noting here that there's no ID here recorded for the log records themselves. This can be done implicitly typically. If you have a log file, of course here you have offsets within that file, and here's offset 0 to offset whatever. And the offset in that file implicitly defines the LSN. So offset is LSN. Offset is the LSN. That is the log sequence number. That is a primary key of the log record. So I don't have to store that key explicitly. The offset gives me that key. So if I'm in this situation, I find this log record that sits here. Let's assume that's a log record and it might have an offset, whatever, 567. Then it might have a backward link here to say 420. Telling me, okay, if I go to offset 420, I find the previous log record written by that transaction. Yeah? So that gives me a backward chaining through the log file. This points to that one, that points to that one, and so forth. If I hit the first log record ever written, this pointer will show to something like null, whatever null means in that scenario. Or maybe it's a negative integer, whatever you deem useful for that. But you have this backward linking, and that's given by this previous LSN number. So we have that. And there's a third field that exists here that is the type of log record. We will differentiate between different types of log records. This is a type, and this is basically something like it's an update log record, it's a commit log record, or compensation log record. We will look at the details in a moment. Those are the kind of fields you find in every log record. So let's look at update log records. What is an update log record? Whenever you do a change to database store, you write out such a log record. Following while, of course, write ahead logging is used, of course. We had a video on that as well. That's another component, another building block we're using here. So we have the fields as above, previous LSN, transaction ID, and here in the type we now signal that this is an update record. Of course, this can be done more efficiently. You wouldn't want to use a string for that. And then there's more information. Then there's a page ID telling you this is the page that is affected by this change operation. That was changed. So again, recall, this implies that the type of log records you're using are at least physical or physiological. Physiological, I explained that in my previous video, but it's not logical. If it's logical, you don't need a page ID. So here, if you write a page ID, this assumes that at least one of the following methods is physical or physiological. I'll go back to that in a moment. Let's first explain the other two fields. So we have a redo information and an undo information. The redo information is information about how to redo the change reflected by this log record. So what needs to be done in the store in order to apply this change again? That is reflected in the redo information. And of course, undo is the inverse. In undo, we keep the information how to undo the change reflected by this log record. Well, then the question is, what type of information is kept here? Depending on whether it's a physical, physiological, or logical logging, you can do different things. What ARIES actually does here, and that makes things pretty complicated, however, it's a pretty clever idea of doing it like that, is redo is actually physiological, and the undo is logical. So actually you could say the page ID is only with respect to the redo information. For physiological logging you need this page. Undo, however, is on a higher level. In the following examples I will assume, however, that everything is physiological, because that makes things physiological. That's how it is written. That makes things a little easier. However, ARIES can be used to be fully logical on undo as well. And that has some advantages, especially when handling concurrency in index structure. So you might be wondering, why the heck do you need logical undo? So a logical undo is really useful for concurrency in index structures, especially B trees. That makes sense, and also allows you to use a variant of ARIES that can adapt its logging level. So depending on the situation you're in, you can run it in physiological logging mode. You could also say sometimes you do a pure physical logging, sometimes you do a logical logging. All of that is supported by ARIES, which makes it a very nice but also a kind of complex method to implement. So for the moment we start with this. That is for the moment. I write it down here, for the moment. But again, you can extend this one. Could be logical, fully logical if you want it. So let's go through some simple logging scenario. How does it work? How would you log something in a database file? So I assume here I have my log file. It's empty for the moment. I have 2 pages I'm operating on, and I use 2 types of log records. You will see that in a moment how it works. Right? We have these structures, the transaction table, we have the dirty page table here, so everything is in place. And we have an initial situation on our database pages. So we have 2 pages, we have a page 42, and they have these values. A is set to 77, B to 55, and so forth. Here's another page, 46. What you see here is a header. We already used that previously to, when I introduced slotted pages, I said, okay, there's some metadata stored here. Typically a checksum could be stored here. But now I also store something different, and that is the log sequence number of the log record applying a change here. In other words, what I write to a page is a version number in a way. These LSN numbers are like versions. LSN is similar to a versioning system in a way. And I write them out whenever I apply a change here. So let's start with a simple change. Let's assume we have a transaction that's running. Here I say this is a log sequence number, so I don't use offsets as explained before. I use logical numbers. That makes the example better readable for the moment. But again, in reality, those are offsets in the log file. So what we see here is this is an update log record. We see it's pointing to null. That is what the dash reflects. So this is the first log record written out by transaction number 1. It's an update log record. It affects page 42. And the redo information says on a logical level, so this is a physiological redo information, that A is increased by 1. Undo does the inverse. It decreases A by 1. So those are physiological log records. And you see what happens if we go back. That is what we were in before. Now when we apply the change, again we use the write ahead logging, which means that the log record is written out first, then the change is applied to the store. And what we see here is the log sequence number of this log record is also kept on the page. So we put it in the head of this page and apply the change here in this field. Before it was 77, now it's 78. That is what happens when applying a change in the database. The log record is written, it's flushed first, it's persisted first, that's important under write-ahead logging, and then it's applied. This change maybe only lives in main memory. It doesn't mean that this change already was written back to the store. So we don't know anything about that for the moment. So we might have a newer version in main memory, a newer version than the one that lives on disk. So let's briefly look at the other structures here. We see the transaction table has an entry for this transaction. That is the last LSN. That was the last record seen. That is number 1. That's this one here. Dirty page table says, okay, 42 has a log record, and that is the first record that might have dirtied the page. This will be useful, especially in the situation when this page is not written back. So if this only lives in main memory but not on disk, then we will later on require this information. That is why we keep it here. So let's write out some more log records here. So there's a second log record that's done by transaction 2. It's also an update log record. And as explained in the assumptions above, it operates on the same page. So there are 2 transactions running on the same page. And what this does is it increases B by 3. That is signaled here. Again, there's no previous log record. And you see, when we go back, that is the initial situation. Now the second log record kicks in and it increases value B from 55 to 58. That is what happens here. Again, the LSN in the header of the page is changed to reflect this change operation. You also see there's a second entry in the transaction table with this last LSN. Worth noting here is this is of course not changed because this is the oldest log record that made that page dirty. This means we are not going to update it here. Even though there's a second change operation, there's no change to this table. There's more logging going on. Transaction 2 has another change. Then we do the same thing. We write the log sequence number out here. In this situation, as we're touching a second page, this page 46 is touched. We have to put another entry here into the dirty page table reflecting that change operation and so forth. Here's another update operation done by transaction 1. So it's again reflected in page 42. Now one of the transaction commits, that is transaction 2, and that means that I can remove it again from this transaction table. So if you go back here, it wasn't committed yet. It's in the transaction table. And that also means this transaction table contains those transactions that are actually running. These are the transactions that have not committed yet. Once a transaction writes out a commit log record, it can be removed. So 2 commits, what happens is we remove it from this transaction table. So that is what happens during normal logging, during normal operation. For every change, you write out these log records to the log file. So there's a third type of log record in ARIES, and that's called a compensation log record. So what is the compensation log record? Again, I wrote down the previous types of log records. The general, or all log records look like that. Update log record looks like this. There's a third type. This is a CLR for short. It has the same fields here. It has type compensation here. And then it's really strange because it has a field that I coin redo the undo information. And it has an undo next LSN. So what do they mean? Redo the undo means this is information on how to redo the undo, which is reflected by the log record creating this CLR. In other words, a compensation log record is executed in the redo phase. However, what it reflects is an undo information. So if we have those 3 phases, again we have analysis, we have the redo and the undo. Let's write it out. Analysis, redo, and the undo. In this undo phase, I undo change operations from loser transactions. For every undo operation, what I do is I write a CLR. I write a compensation log record, reflecting what I did here. Now if the database crashes again while recovering, what happens is those compensation log records will not be looked at in this phase again. So the second time I do the recovery, those compensation log records will be handled in redo. Handles CLRs, which means what originally semantically reflected undo information is now done in the redo phase. I'm redoing this change, which reflects an undo information. Sounds weird, but makes a lot of sense because it also implies that these change operations from loser transactions that need to be undone are only looked at in the undo phase once. Here you keep on writing CLRs, eventually you reach the beginning of a loser transaction and then you don't have to do anything anymore. All the work is delegated to the redo phase, and this is done by compensation log records. This is also important later on if you look at pure logical undos. So the second field is another backward pointer. This is a link to the next log record to be undone for this transaction. This is also very useful for situations where the database crashes while recovering. The value of this is easy to compute. If an update log record wrote this CLR, we set this undo field to the previous LSN of that log record. Let's do an example. Let's assume we are in the situation I explained before. This is exactly the same situation we had above. Let's go back for a moment. So this is where we ended in before. So assume that the database crashes here at this point in time. As explained above, analysis phase has to start from the beginning of the log file, as we do not use checkpointing for the moment. So it reads all of the log and creates current versions of those tables. And it also determines the starting point for the redo phase, which is actually the minimum of those values. I take the minimum, that's called actually the min dirty page LSN. That is the minimum. That's 1, and that determines the starting point for the redo, which unfortunately is again here the starting. This is also the starting of the log, so the redo in this situation would have to start here as well. And redo brings the database back to the state it was in at the time of the crash. So after redo, I'm in this situation here, and I have the pages in the database buffer at least, not necessarily on disk, but at least in the database buffer. That's why I say database buffer here. They reflect the state the database was in at the time of the crash. So with all the log sequence numbers here reflected, I have the transaction tables in this state, the page table in this state, and so forth. And this transaction table now tells me the set of loser transactions. I only have one, that is the loser here. Transaction 1 has to be undone. Now I start undo. And undo starts in backward order from this in this situation. I only have one loser transaction, so I simply look at the last entry here of this transaction, which is entry number 4. That is the first I'm looking at, and I undo this information by looking at this field. That is the field I have to consider now, which means B on page 42 has to be decremented again. So what I do is, before applying the change, again, following write-ahead logging, I write a special type of log record here, and that is the compensation log record. That is what happens here. This compensation log record is written out, and it reflects this undo operation. So there's no redo here. Notice that. No redo is reflected here because compensation log records will be ignored in the undo phase later on. They will only be executed in the redo phase. And that is why I only have one entry here reflecting the undo. This is the information that's being recorded here. And notice that I also decremented here this value B. Let's go back. Before it was 59. Now it's 58, and see that the log sequence number was also changed on this page 42. Let's look at the other values here. You have those two entries. So this points to the previous log record written, which incidentally is here also the same log record that was undone. But this doesn't have to be like that. This is just a simple backward chaining through the log for a given transaction, for transaction 1 in this example. So it's just a coincidence here that this is pointing to the log record that was undone. So this is pointing to log record 4. This is transaction ID 1, and this is the undo next LSN. That is the next update log record that should be undone. This is log record number 1, this one. Okay, so now what happens if the database crashes before being able to undo all of the actions of transaction 1? This may happen in ARIES. So even though you're still recovering, the database system crashes again. So this is visualized here with this cross again. So again, when you're in this situation, what you first do is you read all of the log in the analysis phase. You do the analysis. Then the second thing is you do the redo up to this point, and then you need to do the undo. But what happens is this compensation log record is executed in the redo phase, even though it was previously executed in the undo phase. And then, of course, you have to do the undo phase. You look at this entry, you see, aha, this has to be undone. So you write out this compensation log record for the first update record of transaction 1. That is this one. You see it here, that we have the previous LSN pointing to the previous log record for this transaction. Yeah? And you have here this entry telling you there's no earlier update log record that has to be undone. In other words, the undo process for this transaction 1 is finished with this compensation log record. That is how compensation log records work. So it sounds pretty complex, but it's actually a pretty clever method. If you liked this video, don't forget to hit the like button. Thank you. So if you want to see more database videos, be it in English or in German, take a look at my website datenbankenlernen.de. It has a couple of English and German videos. You can also subscribe to my YouTube channel, Jens did, or you look at our website infosys.uni-saarland.de. See you there!